Got it? All right, I'll begin. Dear Heavenly Father, we thank you for this class again, Lord. I thank you for these students. We thank you for the week about to conclude. And we suspect there will be snow tomorrow. And we thank you for that. Although we would prefer it be canceled sooner today rather than later, tomorrow morning. Oh. I thank you for these students, Lord. I just pray you be with us. Help us to, again, Lord, glorify you in what we do. We never pray, Lord Jesus. Amen. Oh. I don't know, if it's snowing, if the forecast is as it's supposed to be, and it's looking like it's dumped stuff south of here or west of here or whatever, I'll probably cancel class myself. So I expect that we won't have class tomorrow. I would be shocked if we did, really. Okay, so I wanted just to go back and address some claims I made last class. I had a couple minutes last night to work them out, and I was kind of like, oh, these are really, really simple. I should have just taken 2 minutes to do it last class. The other added benefit to it is this little identity is so important. You all know, if you look at sine and cosine, right, that there's a relation between sine and cosine. They're just the same graph shifted, right? And so it comes as no surprise what we're about to derive here. This is what? Sine of pi over 2, cosine of minus theta, plus what? Sine of theta, cosine of minus pi over 2, however you want to write this. Anyway, this is 0, and that's 1. And so, I mean, let me just get to the point. This all is just cosine theta. So sine of pi over 2 is equal to cosine of theta. All right? So this is one of the relations between sine and cosine just directly. They're just a shift of one from the other, right? So the claim that I'm referring to, we're on page 384. What's that? Yeah, these things. He says that inverse sine of x, I'll just remind you guys what the claim is. Inverse sine plus inverse cosine of x is equal to pi over 2. We also had a claim that there's this identity, inverse tangent of x plus inverse cotangent of x is pi over 2. And also that inverse secant of x plus inverse cosecant of x is, again, you guessed it, pi over 2. This collectively is referred to as 7.7.11 in the text, which, of course, is Alice and Hilly edition 10, whatever. Okay. So let me derive these. So y equals to cosine of x, let's say. So that means x is equal to what? Cosine inverse of y. But what else can we say? Oh, I think I've got it backwards. I'm sorry. I'm trying to follow the book and use his letters. He says cosine of y is equal to x. Did I do that? I got it flipped around. Cosine of y is equal to x. All right. I don't want to use different letters as to confuse you when you look at the book. All right, so I'm following the book. So y is equal to cosine inverse of x. Right? But what else do we get to say? Cosine of y is equal to, what is it equal to? Put theta equal to y. We get sine. Yeah. So what? So if you take but this is x, right? So this tells us that sine inverse of x is equal to sine inverse of sine of pi over 2 minus y. But sine inverse of sine of something is what? Pi over 2 minus y. And then if we solve for pi over 2, we got inverse sine of x plus y, but what is y? Inverse cosine of x equals to pi over 2. There you go. There's the first thing in the claim. This is in the textbook. All right. What would so continuing here, what's the cosine of pi over 2 minus theta equal to? We can use the adding angles formula, right? This is cosine pi over 2. Cosine of minus theta. Well, cosine of theta, right? Plus rather. Sine pi over 2. Sine theta. Remember we talked about this the other class. Now cosine of pi over 2 again is 0. And sine of pi over 2 is 1. So what we get is sine theta. So what happens if you look at, for example, well, a couple things we can get from this. One thing we can immediately get is that 1 over cosine of pi over 2 minus theta is equal to what? We can flip this equation, right? 1 over cosine is equal to 1 over sine. 1 over cosine of pi over 2 minus theta. So what does this tell us? The secant of pi over 2 minus theta is equal to what? Cosecant, yeah. But what else? If you divide sine of pi over 2 minus theta by cosine of pi over 2 minus theta, what do you get? You get yourself cosine theta divided by sine theta, right? Using both of the identities I just derived from today. I'm using, let me call this one Pac-Man, and I'll call this one Ghost. So there you have it. The tangent of pi over 2 minus theta is equal to the cotangent of theta. By the way, I think the calculations I'm doing right now are more interesting than what's in the box, and that's why I'm doing them. I want you to see a little bit more how we play with adding angles, identities, and stuff. Because these are the sorts of things we might find ourselves needing to do in future homework problems and so forth. Now, so what do? The same, basically, once you have this identity, these identities I'm about to box in green, these two, this and this, you can derive the second two things in exactly the same way as the sine and cosine inverse. Which one do you want me to do? The tangent or the cosecant? I'll pick one and do it. Which one? The tangent, all right. So what should I do? Same song and dance. We let x equal to cotangent of y, right? Then that means that y is equal to inverse cotangent of x, right? But I also know that cotangent of y is equal to tangent of pi over 2 minus y. So this implies that. And then, by. I need something else. I don't know. Here, I'll try. And then I've been told you need holes, but I'm not very good at. I can't draw holes worth anything, and I've got no yellow markers. But this one. This is my sad attempt at a SpongeBob, but all right. So this tells us that y is equal to, how do I say this? Inverse, what have I done? oh, this is still x, right? So that tells me that pi over 2 minus y is equal to inverse tangent of x. But that tells me that pi over 2 is equal to y plus inverse tangent of x, which of course is cotangent inverse of x plus tangent inverse of x. And there you go. The more important thing about the box 7.711, of course, is that in terms of derivatives, it tells us that the derivatives of the cofunction, the co-inverse functions, are just minus the derivative of the functions, right? It's kind of nice, the simplicity of it. The other thing I was a little bit scared to prove, last time we made a definition, and I said that the inverse secant of x was defined to be the inverse cosine of 1 over x. And I was a little bit leery, like, how can I prove that? Well, I just took a second to try to prove it, and then I was like, well, duh. So prove what? I mean, the claim I made was that what? That the secant of the inverse secant of x is x. Yeah. So why is that true? Let's investigate. Why is the quote-unquote definition consistent with the usual language of inverse function? So if I look at secant of secant inverse of x, then by definition, this is the secant of, what did we say? Cosine inverse of 1 over x. And now it's so embarrassing that I didn't do this yesterday. Just embarrassing. I'm sorry. I take away my right to exposit calculus. I don't know. 1 over cosine of cosine inverse of 1 over x, right? Because secant's 1 over cosine. And what's cosine of cosine inverse of 1 over x? It's 1 over x. And what's 1 over 1 over x? It is x, yes. And a very similar calculation goes through for the inverse cosecant being defined as the inverse sine of 1 over x. So that's what was missing from yesterday in terms of proofs of things. And so I got that out of my system, and we can go on. All right. Thank you for tolerating that. Okay, so let's remind ourselves what we did last class. At the end, we talked about hyperbolic functions, right? We talked about sinh and cosh, right? And let me just restate the definitions for you once more. So, just to let you know where we're going today, I'm going to try to wrap up the discussion of hyperbolic functions here in about 20 minutes or so, and then we'll talk about integration by parts for about 10 minutes, maybe or so, and then we'll take your homework questions. Okay? That's the plan. So, first of all, these were definitions. Cosh of x was 1/2 e to the x plus e to the minus x. Sinh of x was 1/2 e to the x minus e to the minus x. These were respectively even and odd. Yes, sir?
I have a big question because I believe yesterday you put up there e to the negative x equals cosh minus sinh. How was that?
Well, I'll get there in just a second, but I will not forget your question. Just hold on just a minute. Now, hyperbolic tangent we haven't talked about yet. All right, now your question's like a splinter in my mind. I have to get it out. I'm sorry. Let's see here, e to the x. I said e to the x was cosh x plus sinh x. That was what I motivated cosh x and sinh x as being the even and odd parts of the exponential. That's an identity, though. I mean, if I define cosh and sinh as such, then that green identity follows. The other thing I did was I looked at e to the minus x, right? That's cosh minus sinh because cosh is even and sinh is odd. And we multiplied and we got 1. And from that we derived cosh squared minus sinh squared.
That's my identity. That e to the x is just e to the negative x. That's just what it is.
Yeah, that's an identity. These are the definitions. Now, what I was trying to write when I wrote that yesterday is I actually put like under it, that's cosh and that's sinh. And I was trying to motivate these definitions in terms of where it's coming from, in terms of the exponential. But, okay, so, now I don't want to box that. Sorry. All right, so I also mentioned to you the graphs of these like this, right? And like so. Basically, the range of the hyperbolic cosine of x is 1 to infinity. The range of the sinh of x is just the whole deal. Sinh is increasing everywhere. Cosh is increasing for non-negative values, and it's decreasing for non-positive values. I didn't talk about this yet, but what is the hyperbolic tanh going to be defined by? I mean, whatever floats your boats. I would say sinh over cosh is its definition. Of course, you could say, no, it's not. Its definition is it's e to the x minus e to the minus x over e to the x plus e to the minus x, and I couldn't really argue with you. But then there might be other people in here who are like, no, that's not the definition. That's not the definition at all. You're crazy. The definition of hyperbolic tangent clearly should be what? It should be e to the 2x minus 1 over e to the 2x plus 1. Why, do you see why that's, how do we get from the purple to the green? What did I do? Yeah.
Multiply everything by e to the x.
Yeah, we multiply by e to the x over to e to the x. Is there any danger in that? I mean, is the exponential ever 0? Am I multiplying by something that requires, like a side comment? No, exponentials are always positive, never 0. So you can divide by them and multiply them as your heart desires. By the way, that's also true for the complex exponential or the imaginary exponential we talked about last class, because sine and cosine are never simultaneously 0. Mm-hmm. I think the graph of the hyperbolic tangent is a very good question. Now, the reason I wrote that green formula is I think that helps us understand what the graph looks like. See, because we can understand limiting cases from this very easily. Check it out. As x goes to minus infinity, what's this thing look like? As x goes to minus infinity, we have e to the 2x going to 0, right? So this whole expression basically is like minus 1 over 1. Yeah, minus 1. So it's tending to minus 1 as x goes to minus infinity, right? On the flip side, if you think about the limit as x goes to infinity, the 1 and the minus 1 are insignificant, right? And the exponentials totally dominate. So like x going to infinity, we have e to the 2x going to infinity, right? And so the expression is essentially like e to the 2x over e to the 2x, but that's 1. I mean, it's just going to 1. So we've got these horizontal asymptotes of plus and minus 1, all right? And it looks like this. Now, what's the slope of the hyperbolic tangent function at 0? Oh, so by the way, the range of the hyperbolic tangent is what? I don't think I've really proved this per se, but if you add some more analysis to what I'm doing, you can get to it, all right? It seems like it's a relatively educated guess to say the range is going to be minus 1 to 1, though. Okay. Okay, so to figure out what the slope of the hyperbolic tangent is at 0, the natural thing to do would be to calculate its derivative. Let's do that. So let's look at derivatives of tanh and hyperbolic secant of x. Oh no, what's hyperbolic secant? I haven't defined that yet. Oh no. What's this equal to is what? 1 over cosh x. Shall I write them all out?
Are there any that are incorrect?
No. No, like if I ask you what is hyperbolic cosecant of x, you can already tell me it's what? Sinh x, right? And hyperbolic, or coth of x is what? It's 1 over tanh of x, otherwise known as otherwise known as cosh x over sinh x. I think I've got it out of my system now. Is there any more? All right. Sorry, I got to save some energy for physics. All right. So, let's work it out. ddx of inverse tangent, listen to me, inverse. ddx of hyperbolic tangent of x is what? How can I derive this? Oh, for shame, last semester in Calculus 3, I had a derivative of tangent on a test, and people told me, I don't know what to do with this. It made me sad. It made me very sad. What did they learn in Calculus 1? How can you not know how to differentiate the tangent function? I mean, that you're leaving yourself open to attack. Like, you should be wary of the attack of the professor. Like, I don't know. Like, I don't know. I was surprised by that. So, this is not one of those things we have to memorize. I mean, it's not bad to have it memorized once we work it out, but if you forget it, you should be able to, work it out. So this is, I do what, the quotient rule, right? So I've got myself a cosh x times cosh x minus sinh x times sinh x, because the derivative of cosh is sinh and the derivative of sinh is cosh, as we discussed last time, right? And then downstairs, the denominator function squared, so I got myself a cosh squared. Now, you remember one of the identities, so what we got here is we got cosh squared x minus sinh squared x over cosh squared x, like that. Ah, what's that? Now, the numerator is exactly 1, right? So it's 1 over cosh squared x, which is hyperbolic secant squared of x. So there you have it. The derivative with respect to x of inverse, I keep saying inverse, I'm an idiot. The derivative with respect to x of the hyperbolic tangent of x is the hyperbolic secant squared of x. Let's do another one of these. While I'm working on erasing the board, you try, once you've got done copying that down, try to do it for hyperbolic secant and see what you get. I guess I should probably do it over here. Let's see here. dx of hyperbolic secant of x is ddx of 1 over cosh of x, right? By the way, how many of you have Engineering 131 as your Calculus 1? 1, 2, 3, a few of you. How many of you have AP Calculus? Background. How many people here have like Calculus 1 with Sprano? Calculus 1 with Joseph? A lot of you. What else could it be? Young? Anybody with Young? Okay. So, I mean, If you are, if you didn't have Math 131, you might, feel like you're a little bit, like you might have people, you might notice that other people know a little bit more than you do. It's because Math 131 has covered these topics. At least some of Math 131 has already covered. Like Sprano has covered hyperbolics, at least for a day. And I think most of Math 131 has already covered inverse sine and cosine, right? And just generally speaking, I mean, it's hard to put all of AP calculus courses into one bucket, but generically speaking, there's a couple things working against you. One, you probably had it in high school, so maybe it's a little bit dusty. Maybe you had it as a junior or something, right? And so you may feel yourself like a little bit behind. Do not despair. That just means you need to work a little bit harder at the start of the course, right? And if you notice that you don't understand how to do something, like, for example, number 32 in section 7.7, you really need to go back and look at the chain rule and those basic differentiations again, right? If you don't know how to do basic differentiation, you're going to be fighting that. Like, you have to go fix that before you go on. Otherwise, you might not succeed in here. Anyway, do not despair. People have different backgrounds in here, so if you don't feel like you're, same place as other people based on their questions, that may have more to do with your previous experience in calculus and less to do with you as a person. Okay, so just saying. This is the reciprocal function, right? So the derivative of 1 over u is what? Minus 1 over u squared times du dx. So this is minus 1 over cos squared of x times the derivative of cos x, which is what? Sinh x. So you see what we have here. We've got minus sinh over cos times 1 over cos, which is what? Yeah, minus hyperbolic tangent of x times hyperbolic secant of x. So you might notice, hey, there's a difference, right? The derivative of tangent is secant squared, but the derivative of hyperbolic tangent is minus hyperbolic secant squared. Why is that? What's the difference? The difference is, in the trigonometric case, the derivative of cosine is minus sine. And that minus cancels with the minus in the reciprocal's derivative to give you a plus. That's the difference. You want me to write it out? I see at least one person wants me to write out. I'll do it right here. Here's the difference. d dx, I'll do d theta of tangent. I'm tired of writing x. d theta tangent theta, secant theta, d theta, 1 over cosine theta, right? Minus 1 over cosine squared theta times minus sine theta. That's the thing. The derivative of cosine is minus sine, so that gives you like sine theta over cosine theta times 1 over cosine theta. In other words, tangent theta, secant theta, without the minus. Difference being derivative of cosine is minus sine. So there are some signs, SIGNs, here and there that we have to be aware of in the hyperbolic case. Beware. Yes, bueno? Yes, sir? Right. Yeah, they're both plus. Derivative of sine is, derivative of sinh is cos, derivative of cos is sinh. Yeah. Okay, so that brings us to the study of inverse hyperbolic functions. So, so we can talk about inverse hyperbolic cosine of x, inverse hyperbolic sine of x, inverse hyperbolic tangent of x. Now this one is going to be for x, an element of 0 to infinity. This is just for x in the reals. And this is for x where? Yeah, negative 1 to 1. Oh, I'm wrong. Not this one. This one's fine. The first thing I wrote is wrong. Why is it wrong? the domain of inverse hyperbolic cosine, right, has to be the range of hyperbolic cosine. What's the range of hyperbolic cosine? Right? So that can't be right. I have to write 1 to infinity, right? And by the way, we have this. Cosh of inverse hyperbolic cosine of x is just going to be equal to x again for what? Oh, I'm sorry. Other way. I'm an idiot. I get all turned around in these things. I'm sorry. Other way around. Cosh inverse of cosh of x is going to give me x again for x an element of 0 to infinity. What I'm saying is that the inverse hyperbolic cosine is non-negative. In fact, the inverse hyperbolic cosine is really the inverse to the function I'm just drawing in red right now, the graph of that function. See, we can't find an inverse for the whole hyperbolic cosine function because it's not one-to-one, right? It fails the horizontal line test. It hits 2 points, right? So we got to pick either one side or the other to define the inverse hyperbolic cosine for, or we pick the right side. That's the conventional choice. So if somebody gives you inverse hyperbolic cosine of something, the answer that you give back to them has to be a positive number. All right. Well, I mean, anyway, okay, enough about that. Now, so of course we want to differentiate these things, right? So which one do you want to do first, cosh or tan? I'll do two of these. One of them will be tangent, the other one will be cosh or sinh. What do you want me to do? Which one comes first? It's your choice. What's that? Cosh, all right. So what is the derivative with respect to x of inverse hyperbolic cosine of x? This is the question that confronts us. So we set y equal to inverse hyperbolic cosine of x. And then what do? We take the cosh of both sides, right? We get to ourselves to cosh of y is equal to x. It's that same series of steps I made in the last class to calculate the derivatives of inverse cosine and inverse tangent, right? Now, I differentiate implicitly, right? What does that give me? I get sinh of y times dy dx is equal to 1. Because again, the derivative of cosh is positive sinh, yeah. And now I solve for dy dx, what do I get? Yeah, 1 over sinh y, right? Now let's see here, sidebar. Cosh squared y minus sinh squared y is equal to 1, right? So in other words, what cosh y was x, right? So this is really x squared minus sinh squared y equals to 1. Can we solve that for sinh? Let's solve this for sinh. What do we get? Yeah, x squared minus 1, right? Well, that's sinh squared. And then sinh of y would be plus or minus the square root of x squared minus 1, right? Ah, yes. Now that's the question. So when I go over here and I go over here, I got two choices, either plus or minus. Which one does it have to be? Why does it have to be plus? Because the hyperbolic cosine is increasing, right, on the red part where we're defining this to be the inverse function for, right? It's increasing here, so it's got a positive derivative, so I have to choose the plus for this formula. according to our choice of definition for inverse hyperbolic cosine. And there you have it. d dx of inverse hyperbolic cosine of x, 1 over the square root of x squared minus 1. Give it a match. So there's an example. And then, like I said, I'll do the other one. Before I go on, though, are there any questions?
Yes.
Yeah, go for it.
How'd you get x squared? Like that 5 on cos
Oh, right. That's because cos of y is equal to x, so
Oh, okay.
yeah. No problem. Other questions? Yes, sir.
How did you get cos squared y be positive when you subtract it?
Right, so
Oh, never mind.
it's because this inverse hyperbolic cosine is an increasing function, because hyperbolic cosine for non-negative inputs is also increasing. So the inverse function must be increasing if the function's increasing, and that's the case. So what's my first step over here in the next one? Y equals to inverse hyperbolic tangent of x. Then I take tangent of both sides. I get tangent of y is equal to x. Now what do? Differentiate implicitly. That's right. Now that gives me hyperbolic secant squared of y times dy dx equals to 1. Now how do I know that? I was here 20 minutes ago when we differentiated tangent, like so. Well, hopefully not 20 minutes ago. Uh-oh. Does this class end? Oh, okay, phew. All right, let me move on. There's still time. We're good, we're good. But I got to keep going. All right, so we solve for dy dx. It's 1 over secant squared y. Now, this time, now we got to remember if we have, what's the identity? If we've got, I can never remember it. I have to always go back to this one. Cos squared, I mean, I'm not saying you can't remember it. You're welcome to remember it. I just don't. So this is the one I remember, and then I derive the other one. So I want something about hyperbolic secant, so I divide this by cos squared. And I get 1 minus tangent squared y is equal to hyperbolic secant squared y. All right. So, but of course, hyperbolic tangent is x, so this is 1 minus x squared is equal to hyperbolic secant squared y. So that tells me that this is really 1 over 1 minus x squared. And there you have it. d dx of the inverse hyperbolic tangent of x is equal to 1 over 1 minus x squared. And this, of course, is for minus 1 less than x less than 1, because that's the domain of the inverse hyperbolic tangent. I sometimes forget to write those qualifying statements, but you should understand that we are still responsible for them when they matter. Yes, sir.
Use a triangle to determine what value hyperbolic secant squared.
I suppose I could write like a hyperbolic triangle that would be, yeah. I don't want to talk about that right now, though. There is a day for that. This is not that day. That's a very interesting and good question, which I'm going to ignore. Other questions? I'll try not to ignore. Yes, sir.
What's the best way you know that the sign is going to be negative rather than positive, or for normal sign?
I have no way. I have no mnemonic or memory trick. My best advice to you is to be able to derive these things.
Okay.
I mean, I would say read the section, write them down for yourself, try to internalize it. I mean,
obviously, like cos squared y
Yeah, this you got to know.
Second
Yeah.
order range. Okay.
Yep. Things you must know: cosh squared minus sinh squared is 1. The definition of cosh, the definition of sinh. Obviously definition of hyperbolic tangent. These are essentials. Now, this is a wonderful, wonderful formula, because it means, you guys, that all of a sudden, if somebody says integrate, dx over 1 minus x squared, you're just like, oh, well, that's easy. That's inverse hyperbolic tangent of x plus a constant, provided what? Provided x is between here and here anyway. Right? So, bam. Oh, sorry. Can you use your imagination to see it, or can you actually see it?
I can see it.
Oh, okay. All right. Now, there is another thing I should tell you that I probably won't prove today, but I do want to share with you because it's very interesting. There is a relation between the inverse hyperbolic functions and the log function. For example, inverse hyperbolic tangent of x is actually equal to the natural log of, I don't have this memorized yet. Uno momento. I am referring to theorem 7.9.2 on page 394 of your text, where, this is part 3, we learn that inverse hyperbolic tangent of x is in fact 1/2 the natural log of 1 plus x over 1 minus x. So inverse hyperbolic tangent is actually a natural log in disguise. I guess the inverse hyperbolic functions are sort of transformers. Let's see here. Sorry. The robots in disguise thing has been out of fashion for a while. All right, x plus the square root of x squared, I think minus 1. And sinh equals the natural log of x plus the square root of, I think, x squared plus 1. And that's for real x. The second one's only true. This is for x greater than or equal to 1. That's the fine print. The last one, as you would expect, is for minus 1 less than x less than 1. So these are interesting, non-obvious identities, which I'd like to work out sometime, but maybe not today. But I do want you to be aware that there's this connection between the inverse hyperbolic functions and natural logs of algebraic expressions. Very, very neat formulas. By the way, that means that if you don't have inverse sine and inverse cosine, inverse hyperbolic sine, inverse hyperbolic cosine, inverse hyperbolic tangent on your calculator, not a big deal, because you do have natural log. So you could still calculate explicit numerical values for the inverse hyperbolic functions using natural log. Yes, sir?
We need the ranges and domains of these hyperbolic functions and inverse functions. They're not just obvious to me, but
Right.
things that we need to have memorized.
I think if you understand the graphs and if you understand the relation between domain and range, they become natural. So I do want you to understand this picture, this picture, this picture, and what those say about the inverse hyperbolic functions. So I admit, personally, I have to remind myself that inverse hyperbolic cosine is defined this makes sense. So this should be for the range of hyperbolic cosine, which is beyond 1. It's above 1, because hyperbolic cosine is basically kind of like a parabola that opens up, in some sense, that starts at 1. So yeah, I think if you memorize the graph, then you know everything you need to know. How shall I test on these things? These are interesting questions. Don't make me think about this. So, I think that's all I got to tell you about hyperbolics for now. you might ask a question that's I don't think I told you guys yet, but natural question to ask is why do we care about hyperbolic functions, you know? Right? I mean, you guys understand why we care about sine and cosine. You know what they have to do with circles, right? Sine and cosines are very much tied up in questions of circular geometry. Well, hyperbolic sine and hyperbolic cosine are very much tied to questions of hyperbolic geometry. One of the most important examples of hyperbolic geometry appears in physics in the study of special relativity when you study space-time. The thing that's like the distance, we have distance as x squared plus y squared, right? That's the Pythagorean identity. That kind of leads you to the Pythagorean identity for sine and cosine, right? In hyperbolic geometry, the thing that's like that Pythagorean identity is it ends up being like time squared minus space squared. So when you look at the analog of circles in space-time, you get hyperbolas. And Cauchy and Cinch are tied to those hyperbolas, which behave like circles. There's something called rapidity in special relativity. And if you want to understand the motion of if you have two things, if you have like a train traveling with rapidity, say A, and on top of that train, there's some guy throwing a baseball with rapidity B, the rapidity of the baseball with respect to the rest frame is just A plus B. So rapidities add. On the other hand, velocities don't add. Velocities, if you like, what's the velocity of the ball being thrown on the train with respect to the rest frame? It's a very complicated formula. It's not too complicated, but it's like a fraction of the sum of the velocities divided by like 1 plus the product of velocities or something. On the flip side, rapidities add. So the rapidity is like hyperbolic tangent of the velocity divided by the speed of light or something like that. My point to you is hyperbolic functions do come up in physics and other places. Also, if you study, for example, the shape of the St. Louis arc, which has to do with hyperbolic cosine, I think, we have things called catenaries, right? So there's like hyperbolic functions appear in all kinds of solutions to interesting physical problems. They're kind of as basic as sine and cosine, so you should know about them. That's my spiel. All right. So if you'd like to sign up for my newsletter, that's here. So integration by parts. But honestly, folks, I won't try to I won't try to tell you otherwise. I think Cinch and Cauchy are worth studying just for their own intrinsic beauty, and the connection with sine and cosine, that's enough for me. I don't care about those applications that much. So integration by parts is what? It is the analog for the product rule for integration. So we start with the product rule. d dx of u times v. So u and v are functions of x, all right? So du dx times v plus u times dv dx. I think we all can agree, right? Product rule. You guys with me? Hopefully. Take that and integrate. So we have the integral. I'm sorry, one more step. I'm going to solve for this guy. So like u times dv dx is equal to d dx of uv minus v times du dx. I just wrote the derivative second. So then what I do is I just integrate this with respect to x, and I integrate this with respect to x. What do I get? Well, I mean, this already is basically the integration by parts formula. Let me simplify it a bit, though. So canceling the dx's, basically, we get u dv is equal to, what's the integral of, so basically here we have the integral of d dx of uv times dx, right? Minus the integral of v du dx dx. What is this, though? That's just uv minus the integral of v du. And there you have it. This is the famed integration by parts formula. You are now part of an exclusive club that knows about this formula. Do you feel privileged? No? Okay. Just checking. I will now show you the standard example. This is the quintessential example of integration by parts. So here we go. Integrate x e to the x dx. All right, so what I'm going to do is I'm going to tell you what my u and my v are. So my dv, rather. So this e to the x dx, I'm going to make the dv. And the x, I'm going to make the u. I'll write that again over here. U equals to x. dv is equal to e to the x dx. I draw a little organizing box over here to guide my thinking. All right. If I say u is equal to x, what's du? Right? And what's v equal to? V is what? I'm not saying you're wrong, I just didn't hear it. E to the x, right? How did I get from here to here? I integrated, right? What we're using here is the notion of a differential. Remember how differentials work? df, the notation is df is f prime of x dx. So I'm using that all over the place in here, just like you use that in u substitution as a notational guide. All right, so integration by parts formula says uv minus integral of v du. So what is u? U is x. What is v? E to the x. And then I have minus the integral of e to the x du dx. There you go. Hey, that's nice. We know how to integrate e to the x, right? So what do we got? Bam. By the way, you could try to do this integral with u substitution all day long, but I don't know, in short of some kind of very sneaky substitution, it ain't going to happen. So, what's your initial response to this method? It's tight? Oh, it's all right. Okay, I guess I'll accept that. It's all right. Okay. I guess my question would be, as a student, if I could imagine myself being a student. I mean, I'm a student. There's tons of stuff I don't know, and I'd like to learn. How do you choose u? Right, that's an obvious question. Where's the dv come from? Yeah?
I mean, I would choose u based off where I'm going to move it from.
Right. Now that's true, but what can't, tell me something you can't differentiate.
Let's say, for example, 1 over x.
Minus 1 over x squared. No, we could play this game all day long. It's very hard to construct functions you can't differentiate. That's the right kind of idea, but the wrong guy to pick on. The thing that's hard is this step. I have to make the dv something I can actually integrate, right? Yeah. Yeah, well, right, but it doesn't have to be rewritten. I mean, I just made it next to it for the sake of my example not being cluttered. I could write the e to the x before the x. It wouldn't change. I mean, but that's the e to the whatever. The dv has to include. This is true. The dv has to include the dx. All right. Yep.
So if we, instead of doing it that way, if we made dv x dx and we made u e to the x, it would still end up making the same thing.
What would happen? That's a good question. What if we let u? So, I mean, you could do that. I mean, it's an identity. You can try it. So you're saying let this be x dx be the dv, right? And e to the x the u. Okay, so dv then is that. So that means uv would be e to the x times 1/2 x squared, because if dv is x dx, then v is 1/2 x squared, right? And then minus the integral of v du, which would be 1/2 x squared times e to the x dx. Now, there's nothing wrong with what you said. I mean, that's something you can try. But to quote the great songstress, you should dust yourself off and try again. But I'm sorry, I've been watching like 2000, like circa 2000. There's this channel called Bounce. You guys know about this? They play these old movies. It's great. I've been watching all this Jet Li stuff I haven't watched for like a decade. It's great. So anyway, sorry, I digress. Yeah, that's not helpful, right? So, but that's part of integration, especially when you're learning, is to try something. And if it's not helpful, you go, okay, I got to try something else. Now, what's the ultimate answer? So this is somewhat analogous to the question in U substitution. How do I know how to choose the U, right? What's the answer to that question? Yeah, you try something. The ultimate answer, though, is you practice. And you practice, and you practice. And eventually, you know. What's that? Yeah, right. There are some fundamental guidelines, right? You got to be looking to reduce the integral you don't know to ones you do know. So a little bit of forward looking is helpful, right? I know how to integrate exponential. I know how to integrate sine, cosine, certain things. So if what I'm looking at can be changed to that, I'm in a good place, right? There is a useful mnemonic that I'll share with you. This was told to me by students. This is certainly not my invention. I mean, I learned this as a grad student when I taught Calc 2 for the first time. They're like, what about Lyautey? I'm like, what are you talking about? They're like, Lyautey. I'm like, fine. What's Lyautey? It's log, inverse, algebraic, trigonometric, exponential. This stupid mnemonic says you choose. I hate teaching things like this. You choose U in this order, but I will share it with you because it is helpful. Now, as I told the earlier section, this makes no sense to mathematicians because these categories are not mutually exclusive and many questions are begged. But fortunately, you guys are not mathematicians, so this will be helpful. I mean, not yet anyway, some of you. Okay, so, I mean, I'm not a mathematician. I like math. I don't know, name calling, whatever. So in this, I look at this expression. I've got, I'll write it over here. So when we're doing the integral of x, e to the x dx, I look at this. What are my potential? I got to choose u. All right. I go log. Is there a log here? Nah. Inverse. And see, this is where me being a mathematician, or sometimes partly a mathematician, is troublesome because I see exponential and I go, oh, exponential is the inverse function of log. See, but only I would think that. You guys wouldn't see exponential and think, oh, inverse function. There might be 2 or 3 of you in here who are wired wrong like that, right? You might be a math major. Then algebraic. Aha! X is algebraic. So that's why we chose u equal to x. It's fairly hard to find examples that don't fit the overarching guidance of Lyautey. So there is this. Now here, let me show you how it works. Another one, integral of natural log of x dx. So if I follow Lyautey, I go log. Oh, right there. Log. So that is my u. There's no v. But we're not looking for v. We're looking for dv, right? So dv is dx. Oops, sorry. That was redundant. Okay, so then u is equal to natural log of x. dv is equal to dx. At this point, I will tell my dx integration story. So, of course, du is what? Dx over x, right? If dv is equal to dx, v is equal to? X, right? In other words, the integral of dx is x plus a constant, right? I was visiting a school once, and